Hi everybody. Hello. Sorry. Yes, I know I'm a little late. Well, I was not able to find the stream key. Yes. So anyway, I'm here now. Can you all see me and hear me, guys? Yes. No. Am I audible and visible? Can I see yes, no, something in the chat box so that I understand that I'm live? I hope I am. All right. Yes, I am live. Okay. So hello everybody. As I always say, Andariki Namaskaram, Ellargu Swagatam. This is me, your master teacher Nabamita Bhattacharji. And today we are here with another class 11 chapter which is named as States of Matter, everybody. Yes, what is the chapter name? States of Matter. And in this chapter, we actually learn a little bit more about gaseous laws. Okay. In states of matter, obviously, as you all know from the very beginning, when you were just a chotu motu bachu, you would have learned that states of matter, there is solid, there is liquid, and there is gas, right? Now, in this chapter, our major concern is going to be gas. Yes, our major concern is going to be the gaseous state. Because the solid state, we learn about it in class 12. Yes, we also learn about solution, that is liquid state in class 12. But in class 11, we give more importance to gaseous laws. Okay. All right, Arya, thank you so much, Bacha. Thank you so much. Also, you did not have to because you could watch it later. But chalo, thank you so much. Yeah, that's the support. That's a support that I will never ever forget. Okay. All right. So, chalo, let's start with it and let's understand that what exactly do we mean when we are talking about states of matter, right? Something that we know from our age-old classes, isn't it? Like I just said that when we were chotu motu kids, right? When we were chotu motu kids, we got to know that there exists what? Solid, right? There exists liquid, right? And there exist gases, correct? Yes, this is something that we know from a very young age, correct? And we all know that gases, they have no fixed shape, right? They have no fixed shape because whenever you put it, you put it in a room, they will take the whole room. They will occupy the whole room. You put them in a bottle, they will take the shape of the bottle, right? You put them in a bucket, they will take the shape of the bucket. Everybody knows this, right? Very simple, very easy. We also know that they do not have any fixed volume. Boleto. So if you have, let's say, 500 ml of gas in a bottle, right? You had a chotu bottle, you had a small bottle, and in that you had 500 ml of gases. Now, when you pour that gas in a big bucket or let's say a huge tank, do you know what will happen? The gas will actually take, or it will take each and every corner of the whole tank. It will take each and every each and every space that is there, even in the bucket. So that means that we can also say that gases, they do not have fixed volume. Okay, they do not have fixed volume. And once again, this is just a refresh, right? This is just a quick recap of the things that you already know, correct? Yes. Now when we come to liquid, we know that liquids, they also do not have any fixed shape. Am I right, everybody? Yes. For example, if I take some water in this glass, yes, you can see this is copper and it is oxidized. See, it is a little dark in color. It is a little black and green in color. Why? Because copper patina has formed. See, chemistry everywhere. Anyway, so if I take water in this glass, it will take the shape of the glass. If I pour it in a bottle, it will take the shape of the bottle, right? But liquids, they do have fixed volume. And I suppose that you all know this, correct? Yes, I suppose that you all know this, right? Now, when we come to solid, yes, solids, we very well know that solids, they have fixed shape as well as, my dear students, they have fixed volume. Correct? Yes. Yes, everybody. So do we focus on this solid and on do we focus on solid and liquid? Not at all. We are going to focus only on this part, that is our gaseous state. Yes, we are only going to talk about gaseous state. Now, when we talk about gaseous state, right? When we talk about gaseous state, here are also some more properties which that there are certain properties that we come across when we talk about gases. Correct? Yes. What are the properties? The properties, everybody, comes to be, attractive force. Now, fixed shape and fixed volume, or shape and volume, those are also properties. We cannot deny that those are not properties. But we are, you have to understand that we are learning a subject, which is basically chemistry, isn't it? Yes. What topic we will be covering? We will be actually learning about the states of matter, that is solid, liquid, and gas, which we just covered. We will also be learning about certain properties of gases. Yes. Then we will be learning about Charles' law, Boyle's law, Gay-Lussac's law, Avogadro law, and ideal gas equation, and we will solve some problems. After that, in the next session, that is tomorrow we will complete the whole chapter. Okay. Tomorrow we will complete the whole chapter. So I request you all that tomorrow also you will have to come. Now, why are we not able to complete the whole chapter today? Well, that's because that 7 o'clock I have a problem solving class of this chapter. I don't want to disturb that. And today is chain the main, right? And 6 o'clock I have a strategy video that also I don't want to disturb. So about 4 to 5:45 we will complete this, and then we will do the other two sessions. So I'm going to come live thrice. Yes, I'm going to come live thrice, everybody. Yeah. All right, everybody. Shall we move on then? Chalo. So when we're talking about properties, right? Basically not even about properties. Understand this, when we're talking about gas. Yes. Of course, the whole chapter is about gas. And that means that there will be some measurable quantities which will allow us to understand the behavior of gases better, isn't it? Right, everybody? Yes. Basically, like I just said, states of matter, we are going to talk about gases. What exactly are we going to talk about gases, bacha? Huh? What exactly are we going to talk about gases? We will talk about the behavior of gases. How do the gases behave, right? If they have certain amount of mass, if they are introduced to this much amount of pressure, if they have this much amount of volume, if they are introduced to this much temperature, right? If that is the case, if these quantities are provided, then how does the gas behave? That is something that we're going to talk about. And when we are going to talk about, while we are going to talk about the behavior of the gases, there has to be some properties, right? For example, I'm a teacher right now, right? How will you, you will obviously like give me a feedback, right? You're going to give me a feedback or maybe a rating or something like that. I mean, not on YouTube, but if I was taking a paid session, right? What will be the parameters? It will be like, did the teacher know the subject? Was the class fun? Did you get to learn? Were all the topics that you were supposed to cover, was it all covered? These will be the parameters. And very similarly, when we are talking about these gases, we also have to learn about certain parameters. What are these parameters? We talk about certain properties. These properties are attractive force. What do you think? What do you think? What do you think? Do gases have a very strong attractive force? Yes or no? We're going to talk about that. Thermal motion. What if I increase the temperature, or what if I decrease the temperature? What is going to happen? Right? What about the volume? We have spoken about it. I mean, we know in a very vague term, in a very broad spectrum, we know that yes, gases do not have fixed volume. They can change their volume at any point of time. Sure. But once again, science, chemistry, precision and accuracy is our forte, isn't it? We always talk about precision and accuracy. So obviously, we are going to take a look at what will happen if we change the volume this way, if we increase the volume, if we decrease the volume, what is going to happen? Or maybe if we keep the volume constant, what is going to happen? Apart from that, geometry as well. Yeah, geometry as well. Geometry bole to shape. Shape is basically geometry, isn't it? Exactly, my dear student. Now, before we start with this attractive force, everybody, let's go to the little basics of it, okay? Let's understand the little basics that play a crucial role in deciding this attractive force, so thermal motion and all of these. Again, yes, yes, yes. Yes, bacha, I am going to take 2 hours. You think that this chapter is that important? No, this chapter is not that important. But as a teacher, it is my duty to teach you, no? Who knows that there are also those students who want to learn everything. And in this channel, I want to be able to provide you with everything. Once you step into this channel, you should be able to get top to bottom, A to Z, anything and everything that you require in chemistry or in physics or in mathematics, everything has to be there. So I am going to teach you. Now it is on you. You want to learn it, you learn it. You don't want to learn it, you don't learn it. Okay. All right. If it is there in your NCERT, yes, sure, you go ahead and learn it. In JEE Mains, you can expect 1 or 2 questions from this chapter. That means 4 marks to 8 marks can come from this chapter, which is why I'm going to teach you, bacha. Rest is on you. Okay. Rest is on you. Chalo. So let's just jog down the memory lane a little bit. Okay. Now I suppose that you all remember what is intermolecular forces and what is intramolecular forces, right? If you remember, everybody, what is a molecule? A molecule has 3 to 4 atoms, or it can be a little more as well. It can be 2 atoms, it can be polyatomic also. A molecule can be polyatomic, or a molecule can be just diatomic, triatomic, anything it can be, right? So in a molecule, the atoms are either attracting each other, right? And that will be your intramolecular force. Yeah. All right, everybody. And what is intermolecular force? One molecule with another molecule, the force that is keeping them together, that is your intermolecular force. Yeah, Saiteja, don't worry about that here. Don't worry about it. We will be able to cover all the syllabus. Don't worry. We're almost done. How many chapters are there in physical and inorganic? Mostly all covered, right? Once we are done with this, we are left with chemical kinetics, thermodynamics, ionic equilibrium. That's it. Inorganic, though, blindly you trust me, I will take care of inorganic. Don't worry about it at all. I will completely take care of inorganic, and I guarantee you study inorganic from me, you will come back and you will tell me that, ma'am, 20 to 24 marks in inorganic, I got it for you. Don't worry. Your JEE for inorganic, leave it to me. I'll take care of it. And organic also we are starting, right? I just told you that I'm going home. I have to meet my parents. I haven't met them for 1 whole year. Seriously, last I met them was in last year, July, I met them. So I'm going home. That point of time, I will not have this setup, right? I will not have this setup. So what's the point of studying organic on half and half screen? I will be teaching, obviously. I'm not taking leave completely. I'll be teaching, but organic on that half and half screen, it won't be fun. So I'll come back and I'll start with organic and full-fledged. After that, no stopping, no breaks, just organic, 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 organic every single day. Chalo guys, enough talks. Come back and focus, everybody. Yes, please focus, everyone. Okay, please focus. No more talks, everybody. Don't worry about your syllabus. Don't worry about your JEE. Don't worry about which topics we are going to cover. I guarantee you are here. You will be getting everything. You will be getting problems. You will be getting the concept. Everything from the basic, from NCERT to JEE advanced level, everything will be covered. So chill. Take a chill pill, take some popcorn, grab some popcorn, keep a notebook, make the notes and study with me. Okay? Chalo. So first of all, what we were talking about was intermolecular forces and intramolecular forces. Suppose everybody, let's say that nowadays, I'm pretty sure that you guys probably do stay in apartment or society, right? In Bangalore, we have a lot of societies like this, like we have, what do you call it? Like Prestige Meadows and SNN Raj Garden City and all of that. Have you heard of these things? Like where you have like a full-fledged apartment where you have like certain amenities like gyms and swimming pools and blah, blah, blah. Right? Now tell me something. In that apartment society, there are, let's assume that there are 100 families who are staying there. Right? Now, in one single flat, let's say that there is just one family. The family has mom, dad, siblings, right? Yeah. Like my family. Yeah, like my family. I have a younger brother and I have my parents, my mom and dad. So we are staying in one flat. So among us, like me, my brother, my father and my mother, we all have a bond that is holding us together. What is that bond? That bond that is holding us in that one single apartment is your intramolecular force. It is the intra-family force. It is just a bond that is between us family members. Am I right? Yes. But then obviously there are also functions like Diwali functions or New Year or Christmas. At that point of time, what happens? The whole society comes together, yes, and all of us celebrate. You play some music, the kids they dance, right? Or maybe some swimming competition or something like that. Those sort of competitions and everything. What is that? That is a bond that is keeping family, many families together in one society. And that is your intermolecular force. So are we clear with this thing? Yes. What did we just speak about? I'm just writing it down here, everybody. Intermolecular forces. What are intermolecular forces? Intermolecular forces are basically the force between molecules. Okay. What is it? The force between molecules. The force between molecules. All right. Now, I also spoke about intramolecular forces. Please pay attention to the spelling, okay? Intramolecular force. You will be like, ma'am, what is this intramolecular force? Intramolecular forces. Inside a molecule, the forces between the atoms, okay? What did I say? Inside a molecule, the forces between the atoms, the forces between the atoms that keeps the molecule together, that is called as your intramolecular force. All right. Now, intermolecular force, right? This force, this force, everybody, this intermolecular force that you see, do you know that it can be both attractive as well as repulsive? All right. Yes. The intermolecular force, everybody, the intermolecular force, yes, the intermolecular force can be both attractive as well as repulsive. Can be both attractive as well as repulsive. Yeah. All right, everybody. Yes. Now, this attractive intermolecular forces, right? Now, this attractive intermolecular forces, any guesses, my dear student, what are they called as? I'm sure you know. I'm sure you know, everybody. I'm 110% sure. But can you tell me what are these attractive intermolecular forces known as? Anybody? You have heard about it. You have heard about it. Don't you remember ionic, covalent, and then there is another thing. There is another word that is associated. Yes, everybody. Come on. Think about it. Any guesses, guys? Any guesses? Yes. So, I just told you that this attractive forces, it can be both attractive as well as what? Repulsive, isn't it? This attractive force, my dear student, this attractive force, you know what is it called as? This is called as van der Waals forces. What do we call it? We call it as van der Waals force. Yes, this is called as van der Waals force. You getting my point? This attractive force. I'm not talking about the repulsive force, guys. I am not talking about the repulsive force. I'm talking about the attractive force. The attractive intermolecular forces are known as van der Waals forces. Got it? Yes. Shweta bacha, don't disturb no right now. You know that, right? 1 week if I'm taking 12th, the other week I take 11th, isn't it? Yes. So this week we are doing 11th, okay? But 12th I have just now done. There are so many chapters I have completed from class 12th. I have completed what? Electrochemistry. I have completed solutions. I have completed your coordination compounds, periodic properties. All of them are done. So you complete those properly and practice the questions. I will come back to your class 12th also, okay? Today we are going to do 11th class. Cool? All right? Yeah. Okay. Also, you can sit in the class so that, because you know that in JEE paper, you are not going to get only class 12th, yeah? In JEE paper, you are going to get 11th standard also, and 11th standard is 40% of your whole JEE paper. that is physics and chemistry and mathematics. All the three subjects will hold 40% of your JEE paper from class 11. So study. Okay. Now, when we talk about van der Waals force, yes, there are three types of different forces that we get to see in van der Waals force. Okay. What are these three different types of forces here? I'm going to write it down here. Check it out, everybody. The first one that we have to talk about is your London force. Yes, this is your London force. The second one, my dear students, is your dipole force. Yes, and the third one, everybody, is dipole-induced dipole force. Okay, third one is dipole-induced dipole force. All right, yes, these are the three forces that we have to talk about. Cool, everybody? Yes, all right, okay. But before I start to speak about these three forces, tell me, just take a look at this, everybody. Do you see that in case of gaseous state, everybody, in case of gaseous state, everyone, do you see that the attractive forces are almost zero? Almost zero here. So please have a look. Please have a look, okay? We have to take a look at that. Even we have to have a better understanding of that in some time. But just remember this, that attractive forces are here almost zero. It is not saying that it is zero, okay? We're not going to talk about it is zero. Nina, wait up. I'll tell you. Abhi, I'll explain now. Yes, almost zero, but it does not say that it is zero. All right, just remember it, okay? Yes. Now, moving forward, everybody, let's understand the London forces. These London forces, they are also called as dispersion force, okay? Also named as, just like how my name is Nabamita Bhattacharjee, but what do you guys call me? Sometimes you guys call me as Nabamita Ma'am, isn't it? Yes. So the London forces are also sometimes called as the dispersion. Oh, thank you so much, Happy Mowgli. Yes, my mic is working well. You remember, I spent the whole day that day in the office to just fix it. Anyway, so the London forces, they are also called as dispersion forces. Now, to have a better understanding of London force, I am going to show you a picture here, okay? I'm going to show you a picture here, everybody. Have a look at this. I think you will have a better understanding of London forces. Okay. Can you all check it out? Check this out, everybody. Check this out. See what is happening here. Just carefully observe the GIF here. Just carefully observe the GIF here, everybody. Yes? Carefully observe it. Carefully observe it. What is happening? What is happening? So the London force, yes. So Nina, you were asking right away, right, ma'am? What is this instantaneous dipole? This is it. This is it. Okay, this is it. Before you understand London forces, do you remember that example that I had given you, that me and my brother? Remember that me and my brother, you know, when we were younger, right? So there was a point of time when we both used to love CID. CID, you remember ACP Pradyuman, Daya, break the door, Dal mein kuch kala hai, and all of these they used to say. Do you remember that show, CID? It ran for a very, very, very long time, if you remember. Yes, do you remember? So both of us, when we were younger, right? When we were younger, we used to love that show. Okay, we used to love that show. But then obviously at certain point of time, I grew up, right? I grew up and I started to not like that show so much. So I wanted to watch, like, English shows and, like, VH1 and all of that, like English music and all of that. I became a little cool kid. But my brother was younger than me. He was still watching CID. Yes. So now what happened was when we were younger, we both used to watch CID. So there was equal share. The remote was shared between us equally. Yes. Just like how in a molecule, if there are two atoms, if they are distributing the electrons equally, what do you get? You get a non-polar. So when me and my brother, we are watching the same show, we are both watching CID, there is no fight. There is no fight. It's not like one of us is happy and one of us is sad, right? It's not like that. Correct? Both of us are happy. We're like, yay, CID, great. Okay, let's spend some time. Correct? So that is non-polar. Right? But what happened was, when I grew up a little bit and when I started to, When I started to watch all these English shows. Yes, so what happened was at that time, at that time what happened was when I started watching English shows, right? Yes. Today's newborn kids are all cool sticking to that phone. Yeah, possibly. So at that point of time, we did not have phone or anything else, right? Now what happened? So when I became a little cool, we started fighting for the remote. Yeah, we started fighting for the remote because I was like, no, I want to watch something else. And he was like, no, I want something. Now, at certain days, he was a little stronger than me and he could pull the remote towards him. And on certain days, I could like, Mommy, look at him. He's not studying also, not doing homework also, and he's watching TV. I could take the remote. So on certain days, I was happier and certain days, he was happier. Right? Yes. So in those days, what happened was the electron in between in between two atoms. What happened was in between two atoms, the electrons were not shared equally. So a polar molecule. Yes. So now in this case, what happened? Both of us, the siblings were polar. See, we both like he was negative or I was happy, right? He was not very happy. He was sad. I was very happy. The very similarly, when somebody pulls the electrons closer to them, they have a negative charge because electrons carry negative charge, right? We all know that electrons carry negative charge. So when they pulled the electrons, they are showing the negative charge. They are exhibiting the negative charge. A partial negative charge is seen on them and a partial positive charge is seen on the other atom, right? So this is your basic funda about polar and non-polar molecule, right? This London force that we are talking about, this London force is actually, my dear student, it is shown by non-polar molecules. Yes, it is shown by non-polar molecules. Basically, those molecules which both of them are happy. Both of them are sharing the electrons equally. But you tell me something. Now look at this image and tell me something that you all know that electrons are not just sitting like this, like, I'll sit here and I'll just listen to ma'am. Like you guys also, do you think you guys are sitting here just like that? No, not at all. Someone is like, why are you teaching here, ma'am? You don't have any students, only why are you teaching here? Say somebody just commented right now. Yes. Yes, somebody just commented like this. Yes, somebody will be like, ma'am, when are you going to teach, ma'am, that chapter, ma'am? What? Psych, ma'am, today you are teaching this. Very good, ma'am. Amazing, ma'am. Nobody is sitting here with their mind absolutely clean slate, right? You guys are not just sitting here. I know you are distracted. You are distracted. Just like that, even the electrons, they are also hopping around, revolving around. They're not at all in the same place. They're going here. Random movements they are showing. And while they are randomly moving again and again, see what is happening here is at certain point, there is a possibility that all the negative charges have come to one side. Check it out. All the negative charges have come to one side. Let's go back here, everybody. Yes. So at certain point, what happened was all the negative charges, let's say, have come here. Yes, all the negative charges are here and all the positive charges are this side. Now, when the negative charges have come this side, what will this negative charge do? This negative charge will push the negative charges of this other one. Yes, this negative charges that you see, these negative charges, they will push, they will repel the negative charges of this atom. They will push it to this side and here you will have positive charge. And that, my dear student, is here what is happening. Now the negative and the positive, they are temporarily attracting. Obviously, it's temporary. You know, what did I tell? The electrons are moving around. They're not going to sit at one place, right? They're not going to sit at one place, isn't it? Yes. So what is happening here? This is arising only for temporary. And that's why, Nina, what you asked, instantaneous dipole. So this is happening for just a limited period of time, just instantaneously. It happens. There is an attraction and they again start moving and they go back. Yeah? All right, that. All right. Yes? Okay. All right, everybody. Got it, guys? Got it? Got it? Got it? Cool? All right. Yes. So this is what happens in London forces. All right. Now. Obviously, who gave this? Why is the name of the force London? Yeah? Why? Why do you think? Because this force was discovered in London. Because you think that this force was discovered by all the people in the London because they were having something else. Huh? because they were having a party there and they were all moving around. So the Queen Victoria said that, oh, this is the force that we have just realized, so let's call it London force. Do you think that's why they called it London force? Not at all. So there was a scientist whose name was Fritz London. What was his name? His name was Fritz London. Okay, yes, it was given by Fritz London. All right, yeah. Yes, he gave this, and that is why, to respect that he gave it. Now today, if I give you a theory, I would love to call it as a Nabamita theory or Bhattacharya theory, something like that. You know, it should keep my name here, isn't it? Or Nobita theory. I would love to keep it like that. So it was given by Fritz London. This is called as dispersion force. I have told you that also, right? Yes. And I told you, I recently told you that it is shown by non-polar molecules. Yes, shown by non-polar molecules. Yes, all right. Temporary or instantaneous attractive force. What did I say? It is temporary or instantaneous. Instantaneous, yes, force. No. Instantaneous attractive force. Yeah. Instantaneous attractive force. Cool. Yes. And that is called as London force. Now you're going to ask me, so ma'am, what is the relation of the force, ma'am? So we see, and you also see that there are two atoms here, right? There are two atoms. So obviously there is a distance that is acting up. There is a distance that is acting up. So how do we give the relation? The relation is given as, my dear students, that force is inversely proportional to 1 by this distance, okay? This distance, let's call it d. Let's call it d, okay? So this distance, d to the power 6, okay? I think in some books you will also see it as r to the power 6 or d to the power 6, whatever. Yeah, you can also write it as a to the power 6. Just denote that this is the distance and this is what you mean, okay? This is the distance and this is what you mean. So force is given to you as 1 by d to the power 6. Now, Acha, tell me something. So again, one more story. Who was it? This story, ma'am, I can write a book with all of it. Please do write. Please do write, everybody. Acha. Now, everyone, so we saw that, we saw how this one was pushing the electrons, how this one was pushing the negative charges that side, and said that no, attractive force only, right? So what is happening? This is called as polarizing. Polarizing, yes, because these two are becoming polar. Although initially they were non-polar, but for a temporary point of time, they were polar, right? So what is happening? This is called as polarizing. For example, every time I make a strategy video, what do you guys ask? What do you guys ask? Ma'am, if I start from today, will I be able to crack JEE? Isn't that the question that you mostly ask me, right? And then I tell you guys that, yeah, bacha, today, if you start, you can definitely clear it. You have 4 months to go. You do this, you will be able to complete. 1 week later, when I'm giving you another strategy video, you're like, ma'am, if I start from today, will I still be able to clear it, ma'am? Now, what is this? That is your determination. That is your polarizing power. I am doing my work. I am telling you that you gotta do this, you gotta do that, you gotta do this, you gotta do that. You have to complete this chapter, you have to solve this many questions. But what are you doing? You are like, ayyo, ma'am. If I start now, see, it depends on how much you are willing to do. And very similarly, right here also, it depends on the polarizability of the particle. Do they really want to show this? Do they really want to show this attractive force? Yes. So it depends on that, everybody. All right. So what do I write here? I'm going to write here that it depends on the polarizability of the particle. Okay. Depends on the polarizability Polarizability of the particle. Cool. All right. Yes. Yes, Kingpin, you can, but you have to sit with me. You have to come to all my classes. Cool. So, London forces, have we all understood, everyone? London forces, have you all understood? No, bacha, I don't know Tamil. I wish I knew, but you guys can teach me. Teach me. I know that this chapter is Jujupi stuff. That I know. Jujupi stuff that I learned from my students. You guys only taught me. Jujupi means easy, right? So, this chapter is Jujupi stuff. You will be learning. Nina, you're in class 10. Oh, so sweet, bacha. Oh, so sweet. From class 10 onwards, you have started to learn. That's very good. All right. So are we done with it? Everybody, are we all clear with London forces? Should we move on and let's learn the next force that we have to learn, everyone? Shall we? Yes, if this is all clear. Acha, by the way, one more thing is that this is also called as a very short range. Do you see that it cannot really act on something? If I keep the molecules, if I keep the atoms really apart, right? If I keep them in, if I keep them a large distance apart, do you think that the polarizing power will be so much? So no. What do we call them? These are, this is short range force. This is short range force. Remember it. Okay. All right, everybody. Chalo. Moving on. Now let's learn about, let's learn about dipole forces. This is the second type of force. Yeah. So what is this dipole force? Dipole force, I'm pretty sure that everybody knows that this is shown by, this is exhibited by who? This is exhibited by polar molecules, okay? This is exhibited by polar molecules. For example, hydrogen and fluorine. Yes, hydrogen and fluorine. What happens is here is H and here is F. Now, obviously, there is another molecule where you have H and F, correct? Now, on F, you will see that there will be a delta negative here. And on hydrogen, you will see a delta positive here, okay? This is again delta positive and this will be again delta negative. Now, the force that is acting upon these two, this one molecule and this another molecule, these two, the force that is acting between these, the interaction or the attraction between these two, this is called as your dipole force, okay? Dipole force. Clear? Everybody understanding? Yes. Now, why did I write delta? Everybody, I'm pretty sure that you must have seen that we also write delta like this with a triangle, right? So, in Greek letter, just like your English, right? In English, you have alphabets which are capital letter A, small letter A, capital letter B, small letter B. Very similarly, in Greek also, you had, this is your capital delta, the triangle that you see, this is your capital delta, whereas this symbol, this is your small delta. This is your small delta, okay? So, right here that you see this dipole force, this is also nothing but it is called as hydrogen bonding. Hydrogen bonding is a typical example of dipole force, okay? All right here, everybody. Now, why did I show it, okay? Yes, why did I show it? Why did I write here small delta? Why small delta? Why? Why did I not write it as the capital letter delta? Well, obviously because the charge that is there, right? This partial charge or this delta, the small letter delta, it means, it denotes that, okay? It denotes that the charge is actually very less. But very less bole to, what do we mean by very less? Why do we say that it is very less? Well, that's because it is lesser than the electronic charge, which is 1.6 into 10 to the power minus 19 coulomb. It is lesser than that, and that is why we denote it with this small letter delta. Yes, account, you are absolutely right. I think I have just told you this. Now, what do you think? This force, what about this force? Is it stronger than London force or it is weaker than London force? It is stronger than London force because you can see that both of them are polar. Both of these molecules are polar. Once again, this is also a short range order. Okay, this is also a short range force. Now, how do you write the force here, everybody? How do you write the force? Acha, imagine that, everybody, check it out, guys, check it out, everyone. Yes, right here, okay. So imagine that one of the molecule right here, everybody, please check it out. One of the molecule, let's say that these two are rotating like this, okay. These two are rotating like this. You see, this one, this hydrogen, one second, let me move this side. Yeah, this molecule and this other molecule, imagine that they are rotating like this, okay. They are not stationary. Yes, they are not stationary. If they are rotating like this, do you know that the force changes then? At that point of time when they are rotating, the force will be 1 by d to the power 6, same as the London force. Yes, this is for rotating molecule. This is for rotating polar molecule. All right. Now, if the molecule is stationary, if the molecule is not rotating, if the molecule is at just one place, it is stationary, then you know what happens? Then it will be 1 by d to the power 3. What do we write? We write it as 1 by d to the power 3. That means that this is for stationary polar molecule. Gotcha, everybody? This is clear. Till here, is it all clear, everyone? Till here, is it all clear? Yes? Yes, everybody? Yes, guys? Hey, thank you. Hi, DK Edits. Hello, bacha. Welcome to the session. Yes. Yes, okay. All right. Now we will go to dipole-induced dipole force. Yes, dipole-induced dipole force. Why? And what do you think the dipole-induced dipole force would be? From the name itself, we can understand that dipole-induced dipole force means there will be one molecule which is polar and the other one will be non-polar. So this polar molecule will have a negative side and will have a partial positive charge. Now when this comes near it, what will it do? It will ask the non-polar one like, hey, I need attractive force. I need attractive force. So the negative side will push the negative charges to the other side and there will be attraction. So that is your dipole-induced dipole force. Okay, what is this? Let's write it, everybody. Okay, let's write it. I want a different color. I want something like this color. Yes, awesome. See, I'm going to change the color now. See, what is this? Dipole-induced dipole force. What is the dipole-induced dipole force, everybody? The type of attractive force which occurs between polar molecule, one polar molecule and one polar molecule which is permanent dipole moment. Okay, one polar molecule bole to permanent dipole moment, permanent dipole here with non-polar. Okay, with non-polar. I will move from the board just a minute. Okay, non-polar. Okay, that means that this will have temporary. This will have temporary dipole. Understanding, everybody? Yes. So that is your dipole-induced dipole. Okay. Now this also depends upon the polarizability of the permanent dipole molecule. Yes, the one that is polar molecule, that polar molecule, how much is it going to influence the other one? See, for example, right, these days you on Instagram, you have a lot of influencers, isn't it? You have a lot of influencers. What is their job? Their job is to influence other people. Yes. Now there are some influencers who might influence you in a very wrong way, in a wrong direction. But there are also influencers, like even teachers. As a teacher also, I think we are influencers, right? But what are we doing? We are kind of asking you to, bro, study, bro. Make your life better. We are providing you with strategies like, do this and do that. But what happens? Most of us would like to know, where did you get this clothes from? What do you use? Ma'am, which lipstick color do you use, ma'am? Ma'am, where did you get your blush from? What is the polarizability? Your polarizability, the orientation is only different, right? Yes, isn't it? So you are understanding how much are you willing to get polarized. Your willingness to get polarized is more towards the clothes and shopping and car and which laptop to buy and which iPad to buy. But the things that we are telling you right now, which might actually get you the path to buy all these things, that you don't want to follow right now. So you're getting my point? Yes. So the polarizability of the electrically neutral molecule. Yes. Induced dipole moment, it depends upon the dipole moment that is present in the permanent dipole and the polarizability of the electrically neutral molecule. So imagine if you are electrically neutral. Like today, you have come here with a clean slate. You are yet to make a future out of your, you are yet to make a future. You still have a lot of joy, a lot of enthusiasm. There is still a lot of, khali place in your dimag which you can like fill it up with a lot of knowledge, isn't it? Yes. So you are electrically neutral, but your polarizability might differ. And very similarly, just like the other one, yes, just like the other forces, everybody, we also see here that the force here is once again proportional to 1 divided by d to the power 6. And this is also a short range force, everybody, okay? This is also a short range force. Is this clear, everybody? So till here, are we all clear, everyone? Yes. Till here, are we all clear? Yes. Now coming to these two things, attractive force and thermal motion. So guys, we all know, as you can see, that the attractive force is almost zero in gaseous state. Yes. But before we come to gaseous state, do you see that there is also solid state and there is also liquid state? In the solid state, you see that the attractive force is large. Whereas in the liquid state, the attractive force has reduced a little bit. And as you move towards the gaseous state, what is happening? It is almost zero. Now tell me what is happening with the thermal. What is happening? Thermal. What is thermal? Temperature. Right? So basically, when you have solid, that means the temperature is less. Don't take any other example. Take water, na bro. Water has what? Ice is solid. Liquid is pani. Yes. And then you have gas, which is basically your water vapor. Correct. So when you take ice is cold. That means the temperature is less. Yes, that means the thermal energy is very low. So thermal energy is low. That means that intermolecular forces are strong. Am I right? Yes. When the thermal energy is less, intermolecular forces are also very strongly tied. What is the relation that you are getting, everybody? What is the relation? I want it. In 2 seconds, I would require you to tell me that what is the relation here. Now listen. Now, as we go to liquid, what did I do? From ice to liquid, that means temperature has increased a little bit. So the moment thermal energy has increased a little bit, the interactive forces, it dropped down. And then we increase the temperature a little bit more and we have converted the ice to completely gaseous state where the attractive forces are almost nil. So what is it that we see here? Do you not see that the attractive force is inversely proportional to thermal motion, inversely proportional to thermal energy? Yes, I am explaining that only. I am explaining that. What is thermal energy? Thermal means what? Temperature. Thermal means temperature. And energy bole to energy. But you will understand. Listen to me. What am I saying, right? As you go on and on, as you keep increasing the temperature, what happens? The attractive forces are reducing. And the moment we say thermal energy, thermal is definitely related to temperature. Correct? Thermal is related to temperature. But why are we naming it as thermal energy? Actually, what happens when you provide temperature, in any state, in a solid or in a liquid or in a gas, what happens is, now in a solid, when you provide some temperature, the solids, the attractive force is so much that they don't have much place to move, right? Yes, they can only vibrate like this. Correct? Yes. Now, as you go to liquid, what will they do? They probably move like this. Correct? Now, when you say it is gaseous, attractive forces is gone. They probably go like this and they come out of the screen and they are gone. and they probably take a round from somewhere and they are coming back, right? So thermal energy is basically the energy of a body that is arising from motion of its atom. So in a state, either the solid particles or the liquid particles or the gaseous particles, they are also somewhat moving. Obviously in solid, the movement is very less. In solid, the movement is very less, but in gaseous, the movement is very high. So when they are moving, there is an increase in the temperature. There is a certain amount of energy that is correlated with the motion of atoms or molecules. Are you getting my point? Yes. So what did I say? Thermal energy is directly proportional to temperature, but it is inversely proportional to the attractive force. You get it? Now, this movement of particles that I just told you, that because of temperature, what is happening in liquid? Probably they are moving like this. In solid, they are probably just vibrating like this. In gas, they are probably moving and jumping, and whatever they want to do, they are probably doing. This movement that arises because of the thermal energy is your thermal motion. It is your thermal motion. And this thermal motion is the least in solid and it is the most in gaseous state. Am I clear, everybody? Am I clear, everybody? Yes? Yes? Now. 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 Oh, okay. This much is clear, everybody. Can I please have some, can I please see it in the chat? You guys done? Okay. Happy Mowgli has understood. Everybody got it, right? Okay. So we have understood about thermal energy, right? And now we come to gases, everybody. Okay. Now we come to gases. Where are we? Okay. Here. Yes. Now we finally come to gases. Okay. We have to read a little bit about gaseous state. So I told you that in this chapter, we're going to talk a lot about the behavior of the gas, right? Yes. And how do we measure the behavior? Right? Remember I told you that if I was taking a paid class, then obviously you would want to give me some rating or some feedback, right? Yes. And what will be the feedback based on? There will be certain parameters that probably the company that I'm working for will decide. Like right now in Vedantu, you will probably have to give me a rating based on my subject knowledge. How am I teaching? Was the learning fun? Was the learning outcome that you are supposed to get from the class? Was it covered? Yes. Was the teacher rude? These will be probably the parameters, right? So very similarly, the gaseous state, yes, the gaseous state, it also has some measurable parameters. What are those measurable parameters? Those parameters, my dear students, are, okay, those parameters, my dear students, are mass, temperature, volume, pressure, and etc. Cool? Yes? Alright? Yes, everybody? And the behavior of the gas, like obviously, see, in a school, when you go to school, there are certain rules that you have to, there are certain rules that you have to follow, right? Yes? And even me, when I'm working right here, you know, there are certain rules. What are the rules? I'm not supposed to pick up a phone call in the class. I am not supposed to text someone while I'm taking a class, right? Yes, I am not supposed to say anything that might hurt a student. Correct? Yes. Yes, I'm not supposed to give you a false information. These are the things. These are the laws that I have to abide by. And very similarly, these gases, their behavior is also dictated by certain laws. Okay, what did I say? Their behavior is dictated by certain laws which are called as gas laws. Cool, everybody? So let me write that here, that behavior of gases. Let me move this side here. Okay. What was I saying? Behavior of gases are dictated are dictated by certain laws called as gas laws. Okay. All right. Yes. And what are these laws? How did we come across these laws? How did we come across these laws? They were basically a result of certain experiments that many scientists who did it. I mean, if the scientists were not, just if the scientists were not these jobless, if only they had to think about how to pay the bills and how to, get some more money, I don't think we would have to study these many chapters. But guess what? These many chapters we will have to study because NCERT says so, NTA says so, and we have to clear JEE. Right? We have to clear JEE. Correct? So, these were discovered experimentally by many scientists, yes, and these are basically the relationships between what? Basically the relationships between these quantities. You will see. As we move on, you will see that all these laws, they will talk about, these pressure. If we keep pressure constant, what will happen? If we keep volume constant, what will happen? If we keep temperature constant, what will happen? Basically, they will talk about these things only, okay? Yes, now what are the gas properties? We already know that in gaseous state, the force of interaction is almost zero. Remember? Now we go back to this again. See. Now check out all of these. See. Attractive forces almost zero. Thermal motion, random. Volume, it varies with container. Geometry, they do not have definite geometry. They also have lesser density than solids and liquid. Yes, they they exert pressure equally in all direction. They always exert pressure. Yes, all right. For example, you must have seen that. Okay, let me give you an example. Yeah, how do we say that gases, they exert pressure? Have you seen that when you keep a balloon? Let's suppose that it's your birthday and you have blown a lot of balloons, right? And you keep them, and it's a hot summer day. Suddenly you are eating lunch and doop, and you're like, what just happened? What happened? Actually, the volume increased because as you thermal energy, remember, as you increase the temperature, what will happen? What will happen? They move away. Yes, the intermolecular forces are basically what they, the intermolecular forces, the attractive forces are reducing, so the distance between them is increasing. So the balloon burst. And that means that the balloon was trying to escape. It was exerting pressure from inside that I want to expand my volume. Let me go. See, it exerts pressure equally in all directions. Also, if you try to mix, right? Also, if you try to mix one or two gases together, what will happen is they will mix. You don't have to stir them and everything and please mix, no, please mix, no. They're miscible that way. They'll be like, yeah, sure. You put us together, we will all mix up. You put us together, we will all mix up. Okay? All right. Now, based on all of these, are we ready, everyone, to go to the first law, everybody? Shall we go to the first law? But I would require you all to, ma'am, balloon has which gas? Balloon can be having a lot of gas. You can also sometimes put carbon dioxide, sometimes helium. Yes, all right, anything. Hi, Hindustani gamer, welcome to the session. Now, look at it. Yes, what was I talking? See, pressure. We all know that force exerted by the gas on the walls of its container. Acha, okay, a question for you guys, everybody. A question for you guys. Do you see here what is written? What is written here? Force exerted by the gas on the walls of the container. Tell me something. When on the top it is written as pressure, why does it say that it is force exerted by the gas on the walls of its container? Jog down the memory lane. Class 8, you studied force and pressure. There was a chapter in your physics book, no, in your science book, force and pressure. And do you remember what is pressure? Pressure is force divided by area is pressure. Force applied on a unit area is pressure. So that is what it is. So when force is exerted by the gas on an area, what is it? Pressure. The intensity of the force is what? Pressure. It's all written here, everybody. Okay. Volume. Volume of a gas is nothing but basically the volume of the container. Yes. What is temperature? Temperature is the degree of hotness or the degree of coldness of a body that is measured by temperature. Once again, we all know all of these things from a very young age. Correcto? Everybody, till here everything is clinical clear. Now, shall we move on towards our first law, everybody? Once you tell me that you all are ready, I'm going to start with it. Please tell me, are you all ready, everybody? Are you all ready for your first law? Are you all ready for the first law, guys? Come on, I want to see the chat. Are you all ready? Vishal, thank you so much. Yes, that is exactly the formula that I was that I was telling you about. Yes, yes, yes. Dunzo? Hey, guys. Yes, all right. Okay. So the first law, everybody, is Boyle's law. Okay. What is the first law? The first law, my dear students, is Boyle's law. And what does Boyle's law say? The Boyle's law suggests or states that you are going to keep amount fixed. Bole to mass is fixed, everybody. Yes. Bole to amount is fixed. That means mass is fixed, everyone. Okay. Mass is everybody fixed. First of all right. Now you are also going to keep the temperature. See, what were the measurable quantities I told you? Mass, pressure, temperature, volume. You have kept two things constant. Mass and temperature is constant. Once you keep mass and temperature constant, you see that if you increase the pressure, volume decreases. Increase the pressure, volume decreases. Decrease the pressure, volume increases. Obviously. We all know, no, that gases are highly compressible. Do we not know that gases are highly compressible? What are you doing when you're compressing? When you're compressing the gas, what are you doing? High pressure. You are providing high pressure. When you are providing high pressure, the gases, they come closer. The molecules, the particles of gases, they come closer. You increase the pressure, they came closer. They came so close that the volume has reduced. Yes. Now tell me, giving you a very, common example, everybody. In all of our houses, we do use LPG cylinder, isn't it? Yes. We get those red color cylinder from Indian or maybe somewhere else you get it probably. Yeah. Don't you get it? You get that LPG cylinder, right? Now, in that LPG cylinder, okay? Yes. Now, in that LPG cylinder, you must have noticed that in the LPG cylinder, there is how much gas? There is only 14.7 kgs, 14.8 kgs, I cannot very clearly remember. But somewhere, that much amount of gas is actually liquefied and kept it. And that is at high pressure. High pressure. Yes. And everybody knows that what will happen? Anything and everything, just like how money flows from Ambani to me, right? Obviously, I cannot go and tell Ambani sir, Arey, Anil sir, you are not meeting me only. I have a job for you. I'll give you 10 rupees per hour. His bodyguards will pick me up and throw me like this. But obviously, he can come back and tell me that, your college records and everything, your marks and all seem very fine. Would you like to work with Reliance? I'll be like, yeah, sure. Right? Yes. So money, how is it flowing? From someone who has a lot of money and to people like us. We don't have so much money. I'm not Ambani. I'm not that rich. Right? So very similarly, what have you done? In that LPG cylinder, the gas is present in high pressure and liquid. By the way, sorry to burst your bubble, in the LPG cylinder, actually it's not gas. That is the full form, LPG, liquefied petroleum gas. It's in the liquid form. It's in such a high pressure that the moment you switch it on, the gas flows. From where? High pressure to low pressure. Outside the cylinder, it is low pressure. Inside the cylinder, high pressure. So it flows from high pressure to low pressure. Getting my point? So we deviated, but now coming back to it. So Boyle's law says that at constant temperature and at fixed mass, you will see that if you increase the pressure, volume reduces. Did you understand this? Now, how am I going to write that, everybody? You know what? How am I going to write that? Let me take this thing, yeah. Let me take a blank paper here. Where is my good notes? I have a lot of note this thing. Blank. Arre re re. Will it come like this only? Just a second, guys. Just a second. अरे यार. Just a minute, guys. How do I get a new note? Not able to find it. Nothing here. Yes, got it. All right. Check it out. Check it out. Check it out. Hi, BPMC. Yes, yes, yes. Ready, everyone? So what I was telling you was, everyone, yeah, how can we write it? How can we write it, everybody? For example, I just told you that if you increase pressure, volume decreases. So that means that I can very easily write it as P. P is your pressure. P will be proportional to 1 by V. Am I right? Am I right? And from here, from this relation, you can clearly see that if P increases, V decreases. But you can also see that if P decreases, V increases. Am I right, everybody? Yes? Yes? Yeah, I got it. I got it. Yes. Yes? All right. Now, from this formula, I can also write it as, if I have to remove this proportionality sign, right? If I want to remove this proportionality sign, what can I do? I will write it as P is equal to some constant K divided by V, I can write. And this, I can also write it as PV is equal to K. That means that pressure and volume, when you are multiplying, this becomes what? This becomes constant. Am I right? This becomes constant. And from here, if it is becoming constant, that means that if I take now, let's say two different types of gas, and for both of these gases, the temperature and the mass is exactly the same, then what will happen? I will have one pressure, one volume, which will be equal to P2, V2. It will be equal to P3, V3, and so on and on and on and on and on. Am I right? Am I right, everybody? So check it out. This, my dear student, is nothing but, this is your Boyle's law. This is your Boyle's law. Is this clear, everybody? Yeah? Easy peasy biryani tasty? So write EPBT, everybody. All the students who are understanding it, please do write EPBT. That is easy peasy biryani tasty. What do we write? Easy peasy biryani tasty. If you are not able to write so much, just write EPBT. Just write EPBT. All right, guys. Yes, that's it. That's it. That's it. Okay. So this is exactly what was written here also, if you check it out. This is exactly what is written here. See, P is equal to K by V. That means that PV is equal to K. K is nothing but, this is what? This is nothing but a constant, right? This is nothing but a constant, correct? And that means that we will get this. Now, अरे बीपीएमसी, अरे डोंट बी एन एस्ट्रोलॉजर बच्चा, सब होगा, चिल करो, सब होगा, सब होगा, चिल करो. Achha, now that we see that if I take two or three gases, right? If I'm taking two or three gases, what did I say? Didn't I just tell you that temperature is same? If temperature is same, bacha, what do we say? We call it isotherm, right? And these graphs that you see right here, these graphs, they are called as your isotherm, okay? What are they called? They are called as isotherm. Now the graphs are obviously made here, but I am going to make them and show it to you once again. Please practice with me. Practice with me right now, everybody, so that you understand and you will be able to understand this better, okay? All right, so check it out, everybody. What will happen now? Hmm. Yes. Now see. Okay. Now let's check out. Let's draw the graphs, everybody. Okay. Let's draw the graphs. How do we draw the graphs? Let's say that we are going to take one side. Let's take P. Okay. This side is P. And let's take here V. Okay. So if volume increases and if we are saying that pressure, okay, volume is going to increase from this side, right? Left to right volume increases and top to bottom pressure increases. So as you increase pressure, the graph will be somewhat looking like this. This means that, what does it mean, everybody? This means that, one second. This means that as you are increasing pressure, the volume decreases, okay? And in this case, what did I just tell you? Some time back only I have told you here that temperature will be constant here, all right? And what will happen? Mass will also remain constant. Clear? All right, everybody? Yes? Okay. Now moving on, let's draw the next graph, okay? Now imagine we have just taken pressure and volume, right? Pressure and volume. So please have a look, everybody. Please have a look, everyone. You will see that, everybody, that what happens, sometimes what happens is you will find out that in your JEE exam, right, they will not directly give you as a Boyle's law. They will not give it to you as pressure and volume, okay? Yeah, just moved. I have moved the page, okay? I've moved the page. Or chalo, let me draw it here once again. Let me draw it here in this page so that you all are able to see it clearly. Yes? How is it that way? If pressure increases, volume decreases. That's why it will be a graph like this. Yes? So what are you doing? As you are increasing pressure, it is decreasing. Yes? That is what happens. Chalo, now imagine in your JEE exam, they are giving you another different kind of graph. But believe me, this is also Charles' law, okay? Believe me, this is also Charles' law. This time what they are doing is they are taking pressure and they are taking 1 by V, which is exactly the Charles' law. We read that P is equal to, or P is proportional to 1 by V, isn't it? We have just learned that P is proportional to 1 by V. Bacha, graph banana to you will have to learn in mathematics, no? If I now teach you how to make graphs, JEE syllabus will not get covered. Please ask your mathematics teacher how to make graphs. That is Puneet sir. Okay? See, P is directly proportional to 1 by V, right? So in this case, what will be the graph? The graph will look like this. It will be a straight line. Am I right? Am I right, everybody? Now, imagine. So this is also Charles' law, guys. This is also Charles' law. Now imagine you are also given this kind of a graph where you see that this is, let's say, pressure here. And you know what they have taken? They have taken PV. Now what is PV? PV is equal to K, which is nothing but a constant. PV is equal to K, which is nothing but a constant, isn't it? That means that how will the graph look like? The graph will look like this. Just this. Because it's constant. Now, even if you increase the pressure, you know that PV is equal to constant, right? Yes. And that is exactly what we have seen right now. Check it out. This is exactly what is given to you. Okay. This is exactly what is given to you in this slide as well, everybody. Clear hai? Clear hai? All of these things are clear, everybody, with you all? Yes? All right. Now what we have done is, location of straight line and curve changes with the temperature in the isotherm. See, now what we have done is, if you take different temperatures, okay? Yes, if you take different temperatures, okay, let's say that you are taking one temperature that is 200 Kelvin, another temperature 300 Kelvin, but when you are taking temperature 200 Kelvin, you are expecting, not expecting, you are keeping the gas, let's say that you have taken oxygen and you have taken nitrogen. Both of them are at 200 Kelvin. Change the experiment. Now you are taking oxygen and nitrogen, both of them at 300 Kelvin. Change the experiment. You have taken oxygen, you have taken nitrogen, both of them at 400 Kelvin. This way, if you keep changing the temperature like this, then what will happen? Then what is the gas, what is the graph that we will get? So let me write that down here. I'm going to write it down here. Check it out, everybody. I'm writing here that location of straight line. Location of straight line and curve changes. Curve changes with, with temperature in the isotherm. What does this mean? What does this mean now? Chalo, let's find it out. Basically, what we mean to say is, let's say that I make the graph like this, okay? This is my graph. What am I doing? First, let's say that we take the P and V. P and V. Yes. At P and V, are you all able to see it? You are all able to see it, right? So P and V, that means that the first graph, everybody, this graph. What just happened? Everything went off or what? This was our first graph, isn't it? This was our first graph. Do you remember? There was a hyperbola. There was a curve like this, isn't it? Yes, there was a curve like this. So, from here, now see. Now see what we will do. It will be exactly the same. We are just taking 2 to 3 different temperatures. Yes, we are doing it as an experiment and we are just taking 2 to 3 different temperatures. When we take 2 to 3 different temperatures, now what happens is our graph kind of looks like this. This is one. There is this one. And there is this one, let's say. So that means let's consider this to be T1. Let's consider this to be T2. And let's consider the third one to be T3. Okay, and we are expecting that at T1 is greater than T2 is greater than T3. So this will be your graph. This will be your graph. Okay, now let's take the second one. Okay, let's take the second kind of graph that we did, that was between P and 1 by V. P, pressure versus 1 by V. If I take it like this, pressure versus 1 by V. So 1 by V. And this is your pressure. What will I be getting? What will I be getting, everybody? Do you remember? It was straight lines. Yes, it was straight lines. So it will be something like this. Something like this. So T1, T2 and T3. Yes, T1, T2, T3. That's what I'm expecting. Am I not right? Yes. Now imagine if I take the graph to be like this, where I take P versus PV, and I know that PV is constant. That means what will I be getting? I will be getting parallel lines. So T1 here, T2 here and T3 here. Makes sense, everybody? Makes sense? Are you understanding? Are you understanding, everybody? Yes. In this case, I'm saying that T3 is greater than T2 is greater than T1. Because of the graph, from the graph, I can see that this is how it is going to be looking like, right? Yes, from this whole experiment, we have understood that gases are highly compressible. One more thing, we see that density increases, bachos. What happens is density increases. From these graphs, we have understood that gases are highly compressible and we have understood that density increases. Obviously, na? Obviously, isn't it? Yes. See, when the gases were in gaseous state, they were in, their particles were very scattered. Now, when you have increased the pressure and you are bringing them closer, what are you doing? You are bringing the particles closer. If the particles are closer to each other, density will increase. Correct? So, from here, I can also say that, everybody, that density is directly proportional to pressure. Right? right? What did I say? Density increases. Density increases. This is the conclusion of Boyle's law. Conclusion of Boyle's law. Getting it, my dear student? Yes. Good evening, Kevin. Good evening, Bacha. Yes, everybody, are you all getting it or not? Is this clear? Is this clear, guys? Yes? Okay. Now, are you all ready to solve one question? Let's solve a question, everybody. The question is, a spherical balloon of radius 3 centimeter containing helium gas has a pressure of 48 into 10 to the power minus 3 bar. At the same temperature, the pressure of a spherical balloon of radius 12 centimeter containing the same amount of gas will be low. This is going to be so easy, isn't it? This is going to be so easy. It is saying that it has helium gas. Okay, what they have taken? They have taken helium gas, right? And for the first case, they have given you the radius. For the second case also, they have given you the radius. For the first case, they have also given you the pressure. For the second case, they have not given you the pressure. So what do you have to calculate? You have to calculate the pressure, isn't it? Yes. So very simple, very easy. We know that we will have to use P1 V1 is equal to P2 V2. Am I right? Yes. We have to say we have to calculate P1 V1 is equal to P2 V2, and that means what is our P1? P1 is given to you. Everybody see 48 into 10 to the power minus 3. Yes. So very simple, very easy. What will I write? 48 into 10 to the power minus 3. What is my volume? Volume is going to be, it is a sphere. It is a sphere with a radius 3 centimeter. That means that 4 by 3 pi r cube, isn't it? 4 by 3 pi r cube. What is r? R is 3. So 3 cube. This will be equal to P2 multiplied with 4 by 3 pi 12 to the power 3. Isn't it? Yes, am I right? Okay. So I can very easily 4 by 3 pi, 4 by 3 pi I have to cancel because both the sides it has the same thing. Right? Very good. Now see what do we have? Now what do we have is, yes. Is it 4? No, bacha, it's not 4. It's not 4. Calculate. Check it out. 48 into 10 to the power minus 3 into 3 3s are 9, 9 3s are 27. So I can clearly write it as 27 divided by 12 into 12 will be 144 and 144 into 12. Chalo, let's write it as 144 into 12. That means 3 4s are 12 and 3 9s are 27, isn't it? Is equal to P2. Can somebody calculate this? What is P2? P2 will be equal to what? Anybody? Can you all calculate? Chalo, let me only use my calculator. I think I'll have to use my calculator. I won't be able to solve it. But you guys, you are supposed to solve it. Okay? You guys, you are supposed to solve it. What is it? 48 into 9 is equal to this divided by 144 into 4. This is 0.75. 0.75 into 10 to the power minus 3. P2 is equal to 0.75 into 10 to the power minus 3. But see, in the question it is written 10 to the power minus 6. So if I have to bring it to 10 to the power minus 3, I can also write it as 750 into 10 to the power minus 6. Am I right? And this, my dear students, becomes your answer. Okay? This, my dear students, becomes your answer. Please check it out and let me know. Are you all also getting the same thing, everybody? Yes. Are you guys getting the same thing? Yes? Are you all getting the same thing? Hello, Mani. Welcome, welcome, welcome. Where are you? You have just come from coaching or class. I suppose 750. Vishal is also getting 750. Abhiram, check it out, huh? Abhiram, how I have solved it. Please check it out once, okay? Chalo guys, moving on to the next one is your Charles law. Acha, all this time what we did was we kept temperature constant, which is why we got isotherm. Do you remember? We got isotherm because we kept temperature constant and mass the mass constant, amount constant, and we varied the graph with respect to pressure and volume. This time, what if we keep the mass to be constant? Okay, let's keep the mass to be constant, and along with mass, let's keep pressure constant. Okay, let's keep our pressure and mass constant. Now, once we keep pressure and mass constant, what will happen? The volume occupied by the gas is directly proportional to temperature. You increase temperature, volume increases. Decrease volume, decrease temperature, volume also decreases. So that means that once again everybody, what can I do? Can I not write it as everybody? Okay, now we are going to do Charles' law, everyone. Okay, here is your Charles' law. So Charles' law suggested that if you keep pressure constant and your mass constant, what will it be? It will be, see, volume is directly proportional to temperature, right? We will have volume is directly proportional to temperature. And if that is the case, that means if I just have to remove the proportional sign here, I can definitely write it as V is equal to KT, right? Yes, Mani, tell me. Achha, very good, yes. Or I can write it as, everybody check it out, I can also write it as V divided by T is equal to K. That means that it is just a constant. It is just a constant. Am I right, everybody? And if that is the case, then what is the relation that we will get? The relation that we will be getting is V1 divided by T1 is equal to V2 divided by T2. Am I right? Am I right? Yes. Yes. Very good. Very simple, everybody. All right. Let's add another page here. Now, if I have to draw the graph, okay? We'll do one. Okay, Mani. Okay, we will try to do that. Okay, we will try to do that. Chalo. Now, imagine that I have to draw the graphs. Not imagine, I am going to draw the graph. Okay, now what will happen is, obviously very similarly to the last one, we are going to keep temperature like this and we are going to increase the volume. Now, what will happen? This graph looks a little bit like this and then there are dotted lines. Any idea why we have the dotted line here and we also have a solid line here? Well, that's because, my dear students, that's because, everybody, you have to understand that when you take the temperature to very, very, very low temperature, you tell me, guys, that you tell me, side, please let me know, everybody, that at very low temperature, can the gases exist as gases? Nope. Yes, at this point that you see right here, we are saying that volume is supposed to be 0. And this, my dear student, is a hypothetical or imaginary temperature. What is it? It is the lowest temperature, but this is a hypothetical or imaginary temperature. Yes, because at this temperature, usually we will see that gases don't exist as gases. They liquefy. Yes, and you know what this temperature is called as? This is called as absolute zero. This is called as absolute zero. Yes, yes, and this absolute zero temperature is minus 273.15 degree Celsius. Okay, minus 273.15 degree Celsius is a very, 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 I mean, how do I say it? It's a very cold temperature, correct? It is such a cold temperature that gases will not be able to exist at all. There is no possibility that gases will exist at this temperature. Correct, everybody? You're getting it? Yes? All right? All right, everybody? Clear? Now, who is this? There will be someone who will always, Have you asked him? No, but you will disturb my session. Go and ask him and see what he says. Okay, got it, everybody? Yes, so this is called as, now from here we understood that we will have to introduce a new scale, and that is your Kelvin scale. At this temperature, what we say is that 0 degrees Celsius will be equal to 273.15 Kelvin. And many a times in your problems, yes, when you are given a problem, you will see that this 273.15 Kelvin, right, it is just noted as K. It is just noted as K. Got it? All right, everybody. Yes, is this understood? Is this understood? Let's go to the next law. And the next law, everybody, is the next law, everybody. Acha, by the way, these are called as isobars. Why isobars? Because temperature is same, na? The last one was isotherm. This one is isobar. And the next one will be our isochore, because this time we are going to keep the volume constant. Okay, we are going to keep volume constant, and we see that pressure is directly proportional to temperature. So P by T is equal to constant. That means that P1 divided by T1 is equal to P2 divided by T2. Same thing, same everybody. Yes, now you can look at the graph also. What is the graph? How will the graph look like, everybody? Very simple, very easy. As we have already done it, you can clearly see that this, what is it? Gay-Lussac's law. Here you will see that it will look like this. If I have temperature here and this is my pressure, what will happen? This is how my graph will look like. Okay. This is how my graph will look like. Clear hai everybody? Yes. All right, everybody. Now moving on from here, let's quickly go to Avogadro's law. You know, these things you have already studied. Remember mole concept, some basic principles. Yes. In some basic principle, we have learned about those 5 laws that govern all the combinations and everything, right? So Avogadro's law, we know that at equal volume of all gases, yes, if you take equal volume, let's say 1 liter of oxygen, 1 liter of nitrogen, and the temperature is also same. Yes, temperature is also same. Now, you know what I will expect? I will expect that the pressure that is containing, no. I have taken 1 liter of oxygen, 1 liter of nitrogen. Temperature is, let's say, 300 Kelvin. Okay. Temperature, let's say, is 300 Kelvin. Let me draw it. Okay. Let's say that I have this container. In this container, what have I taken? This is the layman's term. In no book, you will probably find this because it does not actually come up to this, but this is just layman's term. Okay. Let's say 1 liter of oxygen I have taken here. And here I have taken 1 liter of nitrogen. Okay. Both of them have temperature, let's say, 300 Kelvin. And let's say pressure is also equal to 1 atmospheric pressure. Okay. At this scenario, we will see that the number of molecules, okay, we will see that the number of molecules will be same. Yes. Number of molecules of both the gases will be exactly same. All right. That is what we will see. Number of molecules will be equal. And that number, that is Avogadro number, everybody knows this as well, right? 1 mole of a gas is equal to 6.022 into 10 to the power 23 molecules. That is your Avogadro number. At STP is standard temperature and pressure, where temperature is 273.15 Kelvin and pressure is 1 bar atm. Yes, at this point, what will you have? You will have it as 22.41399 liter of volume. Okay, this will be the case. Now, after reading all these laws that we have come up, okay, so we have come up with many laws, right? Yes. Now imagine, as a student, even you have to follow a lot of laws and lot of rules when you go to school or when you go to coaching institute, when you take an exam, right? You have to follow a lot of rules and regulations. So if you submit your homework at the right time, if you listen to your teachers, if you respect your teachers, you will be called as an ideal student, isn't it? And very similarly, my dear students, what happens is here also, when a gas that follows all these laws, which are the laws? Charles' law, Boyle's law, Gay-Lussac's law, Avogadro's law, when they follow all these laws, which they don't, because none of you are ideal student as well, right? Yes. So ideal gas, yes, ideal gas is actually theoretical. It's hypothetical. Doesn't exist. But we talk about it because obviously if we don't make the set of laws and rules, how will we understand the behavior, everyone, isn't it? So what do we say? We say that a gas that follows all these laws all these laws, yes, they are assumed to be, or they are called, yes, they are called ideal gas. Okay, they are called as ideal gas, everybody. Okay, all right. And you know why they do not exist? Why did I say that they are hypothetical? Why did I say that they are hypothetical? They only exist in theory. That's because whenever they are when we suppose that this is an ideal gas, we are also trying to say that the intermolecular forces are not present. But remember, I showed you that chart and I kept telling you that it is almost zero, almost negligible, but it is not negligible. Am I right? I have told you that. Remember, I showed you that chart and I kept telling you that it is almost zero, almost negligible, but it is never zero. Okay. So that is why we actually only have, what do we have? We have real gases. We actually have real gases. Okay, we have real gases. And these real gases, my dear students, they do not follow the gas laws. What they do is they always deviate. Okay, only for a very small certain temperature or very small certain conditions, they will behave like, yeah, I'm an ideal gas. But you know, the moment you let them go, they will behave like, no, I'm a real gas. For example, you know, when you go to your school and there is no teacher around, what do? Yeah, everybody tries to make all the shore sharaba. You all shout, you make it look like a fish market. And then suddenly when you see that your class teacher or your principal ma'am is on a round, everybody is shh, you behave like an ideal student. See? But the moment you remove those conditions, you change the conditions, you are no longer an ideal student. You change yourself to be a real student. So very similarly, these gases, the real gases, what happens is they also behave like an ideal gas, but only for very small, very certain conditions only. Very particular certain conditions are there. At that point of time, they act like an ideal gas. Otherwise, they don't. Okay. So, for example, at a very low pressure, yes, if you have a low pressure, then yes, the real gases, they will follow Boyle's law. But the moment you increase the temperature, do you know what happens? They deviate. They're like, nah, that's enough. I don't want to follow. They will become like a real gas. Yes, the real gases, they also, they do follow Charles' law. But the moment you have very high pressure and low temperature, they'll be like, nah, I'm fine. I'll be ideal gas. Now, from combining all these laws together, we have come up with a formula, which is basically your PV is equal to nRT, and this is the formula which we usually use to always solve every problem. Knowing this is very important because this formula is used in many chapters. Okay, so do not let go of this. Please do learn this. Okay, this is your ideal gas equation, everybody. Now, do you remember that we also spoke that pressure is directly proportional to what? Pressure is directly proportional to density. Do you remember? So from there, I can also write it as, see, I can also write it as PM is equal to DRT. Okay, and all the explanations are here. PM is equal to DRT. P is pressure, M is your molar mass, D is your density, R is your gas constant, T is your temperature. So chalo, let's solve a question, everybody. Okay, time for some questions. After this, I have to stop the class. Then we have to go for the next session. I also have a strategy session that is coming up. All right. So what is given here? You are given that a 0.5 moles of gas A and X moles of gas B exert a pressure of 200 Pascal in a container of volume 10 to the power meter cube. No, 10 meter cube at 1000 Kelvin. Given R is the gas constant in in joules Kelvin Kelvin to the power minus 1, mole to the power minus 1. What is X, everybody? Okay, what do you have to say? You have to say what is X. All right. Yes. Okay. Chalo. Oh, hi, Nina. No problem. You can always watch it. Okay. Yes, you can always watch it. Mani, I'll tell you, I told you, no, I will record all the trends and exceptions of periodic table very soon. I will do that. Okay. I will do that. Chalo. So guys, let's solve it everybody. What are we given? We are given that N is equal to, and N is basically moles. Okay, what is moles? 0.5 plus X is given to us, right? Temperature is given to us as 1000 Kelvin, right? V is equal to 10 meter cube, right? P is equal to 200 Pascal, isn't it? So that means what do we have to follow? PV is equal to nRT, everybody. What do we do? PV is equal to 200 into 10 is equal to 0.5 plus X, yes, multiplied with R, we just keep it as R, and T we know it is 1000, isn't it? Yes. So let's just cancel 1000 this, 2 and 0 cancel here. So 2 is equal to, let's write 0.5 as half plus X, and let's take the R this side. So it will be 2 by R. Correct? Yes. Yes, it will be 2 by R. Very good. Now what we can do is 2 by R is equal to 1 plus 2x. Correct? So that means I can write it as 2 by R minus 1 is equal to 2x. Correct? That means that I can write it as this 2, I can bring it here. Right? This 2, I can bring it here. And I can write it as, no, let's say that I multiply 2 both the sides. Yeah, let's say that. This side also I have 2 and this side also I have 2. So 4 by R or 4 by 2R minus R is equal to X. So that means that option D is the correct answer. Please check it out everybody. Is this the answer that you are getting? Please check it out. Please check it out everybody. Yes? Laughing at the chats that you guys are sending. Guys, I think I'll have to push my session, the strategy session a little bit. I think let's push it to 6:15, I guess. Let me tell my CM. Okay, done? Yes, everybody got it? Everybody got the answer? Same answer you guys got it? Chalo then. Yes. Hi Rahul. Hello. Welcome. Chalo. Moving on to the next question. The next question is, for 1 mole of an ideal gas at constant temperature T, the plot of log P against log V is, P is pressure, V is volume. At constant temperature, the moment they say constant temperature, but choose what law can you imagine? Constant temperature means Boyle's law, right? What does Boyle's law say? Boyle said that PV is equal to constant. Yes, PV is equal to constant. Hey, stop and study, bro. What are you doing? Seriously, dude, study. I'm teaching you. You don't have to do all of these things to get my attention. Yes, you could have just said hi and I would have responded. Shh. So what did Boyle say? Boyle said that PV is equal to constant. Acha. Now, can I write also that log P plus logarithm operations, P multiplied with V. That means that log P plus log V it will be, right? Log P plus log V it will be, isn't it? Yes. So log P plus log V is equal to also constant. Am I right, everybody? Very good. So that means I can write it as log P is equal to minus log V plus constant. Am I right? The moment I see minus here, that means that what will I be getting? I will be getting a graph that somewhat looks like this. Yes, that somewhat looks like this, everybody. That means it is a straight line with a negative slope. So option C is the correct answer. Gotcha, everybody? Yes, is this clear, guys? Is this clear? Let me know. Is this clear, everyone? You guys are getting it? Chalo, moving on to the next question, everybody. The next question is, assuming ideal gas behavior, the ratio of density of ammonia to that of hydrogen chloride at same temperature and pressure Okay. Same temperature and pressure, guys. So what do we know? We know that PM is equal to DRT, right? What do we know? We know that PM is equal to DRT. That means that I can also write it as the D is equal to PM divided by RT. Clear? Right? Now I know that M of molar mass of NH3. What is the molar mass of NH3, everybody? It will be 3 hydrogens. So 3 plus 15, no, 15, 16, 17, 17, right? And what is the molar mass of HCl? 35.5 plus 1. So 36.5 U. Am I right? Yes. Now I know that if D is equal to PM by RT, then that means that they will be in a ratio. Yes. So I can write it as DNH3 divided by DHCl is equal to, what will it be? Molar mass of NH3 divided by M of HCl is equal to 17 divided by 36.5, which will be, come on, now tell me the answer. I think it will be equal to almost 0.5, almost equal to 0.5, because 17 multiplied with 17, another 17 will be around what, 35. If it is 36.5, that means that option B, 0.46, it should be ideally, right? It should ideally be 0.46. Am I right? Oh, yes, finally. I think this is where we end because it's about to be 2 hours. And I really believe that after 2 hours, your mind stops working absolutely. And you are probably not able to understand anything. So, everybody, please just check this answer. If you are getting the same answer, that means you are right, everyone. And with this note, thank you so much, everyone. For today, we are finishing the session here. But in the next session, we will be doing this problem. Yes, we will start with this problem. Then we will understand Graham's law of diffusion. Yes, then we will do some more problems. We will understand kinetic theory of gases, the postulates, different types of molecular velocities, and a lot of other things. And basically, tomorrow we will be completing the chapter, everyone. So all the students who have come here today, who attended the session today, please do come tomorrow, because tomorrow is when we are going to do the bigger chunk of the chapter, and this bigger chunk of the chapter are the topics from where you can expect questions from JEE. So don't miss tomorrow's session, everybody. I will be expecting you all. Okay. With this note, thank you so much. Oh, without you, I would not have been a teacher. It's because you choose to learn from me. I am your teacher. Thank you so much. I'll see you very soon at around 6:15. I'll see you with my strategy sessions. Yes, and I'll tell you about some of the very important chapters that you must do to be able to get 99 percentile. All right. So I'll see you there as well. With this note, stay tuned to the channel. If you like this video, don't forget to share it with your friends and